cosmic backgrounds. And today I would like to explore this third possibility on how we can use cosmic backgrounds to constrain FIPS and notably axion-like particles. So axion-like particles in their minimal models can couple with photons, thanks to this well-known Lagrangian term. And this is just a sketch of the parameter space where you have the ALPs photon coupling as a function of ALPs mass. As you see that the range of interaction strengths as well as ALPs masses is very broad and is probed by cosmology and stellar evolution as well as laboratory experiments. And there is a corner of the parameter space where axion can have masses around nano up to the microelectron volt that is probed by high energy astrophysics and notably by gamma rays. And this is what will be the focus on my talk. So if you consider the production of axion-like particles in core collapse supernovae, and you consider that axion-like particles can couple with photons only, then the main production mechanism will be through Primakov effect, where thermal photons are converted into axion by feeding the strong electrostatic potential of the ions and the electrons. So you can compute what is the expected rate of ALPs emission from the supernova core, which depends on time after the bounce during the core collapse, and also depends on the progenitor mass. So this rate of production, if you consider galactic supernova, then is directly related to the final flux of axion-like particles that are emitted from the supernova by the scaling with distance squared. But then if you want to go from there to the expected gamma ray flux, what occurs is that thanks to the very same coupling between photons and axions through a magnetic field, what occurs is that while being emitted into the interstellar medium, the axion-like particles feels the presence of the strong magnetic field of the galaxy, and then what occurs is that they can convert into photons, and those are the photons that we want to target and the photons that may be directly observable. So in a very simple approach, if you have a monochromatic ALPS beam traveling into a magnetic field, then the conversion probability of the ALPS beam into photons is proportional to the transversal component of the magnetic field and the coupling of of ALPs and photons. And in a more sophisticated way, then you can solve the propagation equations numerically and compute this probability by numerical integration. And if you consider specific model for the magnetic field of the galaxy, then you can get maps such like that one, which is in galactic coordinate. You have the longitude running here along the galactic disk and the latitude here above and below the plane, where you see that the color scale represents the conversion probability of this ALPS beam into photons. So one of the main perhaps takeaway of this talk is that any axion-like particle search that relates to the ALPS photon conversion in the galaxy is affected by our uncertain knowledge of the galactic magnetic field, because what we are actually sensitive to is really the product between the ALPS photon coupling and the transversal component of the magnetic field. But let's suppose that, okay, you can compute this probability conversion, then what you can see here is that in the massless case, this probability conversion is basically mass independent. So there is a one-to-one correspondence between the energy of the emitted ALPs and the energy of the final photons. This means that the range of energy relevant for photons observations is the realm of are the X-rays and gamma rays. So between, let's say, tens of MeV up to 200 MeV for this specific signal. And if we then compare with what is the current stage and status of gamma ray astrophysics, here is a summary plot of the sensitivity of different instruments as a function of energy, where we see that the low energies below the TV scale are led by telescopes that are on satellites, while at the highest energy we rely on ground-based gamma ray telescopes. And in the energy range where we would like to see an ALPS signal from core-collapse supernovae, then there is a sensitivity gap, which is called the MEV gap, because we have only basically two main instruments, so the spectrometer aboard the integral satellite, which touches upon 8 MeV at most, and at the higher energies, here at 100 MeV, we have the starting of the sensitivity of Fermi-LAT, which is anyhow degraded here by the high cosmic ray contaminations and the low instrument performances. So we have to deal with what we have and try to use those data to set constraints on axion-like particles. So from core-collapse supernovae, if we just consider a single event, then these emissions would basically show up as a short burst with an energy spectrum, as I showed, peaked at 100 MeV, more or less, with specific time-dependent spectral signature. And this is what we would like to target with the search. Nonetheless, you have to consider that the probability that you see a supernova explosion within the field of view of the telescope is low and depends on the pointing strategy of your instrument. So luckily enough, for supernova 1987A, there was a telescope on a satellite, so the gamma ray spectrometers aboard the Solar Maximum mission, that was pointing to the sun, but eventually it may also have been sensitive to photons coming, traversing from the side, the instrument, and coming from supernova 1987A gamma ray burst. So in the lack of a detection, strong constraints were set. Geographic also had a discussion about it, but those are the leading constraints for masses around the nano electron volt and below that comes from the fact that this gamma ray burst was not observed. You can also use extragalactic supernovae, and this was actually done in the recent past by targeting 20 optically characterized supernovae, so usually using the optical light curve to reconstruct the explosion time, and then from there look for gamma ray bursts in the Fermi-LAT data, so just looking at time-dependent signals close to the explosion time. And again, in the absence of any clear gamma ray burst in the correspondence of this supernova explosion, then Mayer and collaborators could set an upper limit on the photon coupling as a function of the mass, which is kind of a factor of few weaker of supernova 1987A, but represents an important step forward in the understanding of this part of the parameter space. So another way to exploit the ALPs production from core-collapse supernovae is to look for the cumulative contribution from past core-collapse supernovae. So this idea was initiated in the context of axions by Raffelt and collaborators, but this signal in terms of gamma rays is suppressed by the galactic conversion. Instead, what occurs is that if you consider axion-like particle productions, then you can open up a sizable portion of the parameter space by considering the flux of axion-like particles, which is emitted by all core-collapse supernovae in our universe. And so you have to convolve the time-integrated core-collapse ALP spectrum with the core-collapse supernova rate as a function of redshift to get basically the cumulative signal over redshift space of this ALPs production from past core-collapse supernovae. So we have addressed this problem in two works, one led by Pierluca Carenza and one led by Christopher Reckner and Francesco Sivo, trying to refine the analysis of this type of signal and try to set constraints with Fermi-LAT data. So as for the time-integrated spectrum, what we have done was actually to go beyond the approximation that was done until recently, to use only one progenitor mass for the supernova core collapse event. We had several simulations that we exploited in different mass ranges. Part of them are leading to a successful core collapse explosion, but we also included the modeling of the so-called fail core collapse explosion, which leads to the formation of black holes, as Georg also explained yesterday. So if we consider then the production of axion-like particles as a function of energy for the different mass progenitors, we have different spectra and different intensities for the flux that are predicted. So this allows us, by interpolating between the spectra, to compute the time-integrated spectrum by fully averaging and weighting over the mass range by a given mass function. And there is, however, an important uncertainty here, which is the fraction of failed events. So we don't really know what is the fraction of core collapse supernova that leads to the formation of black holes. And so we study parametrically what is the effect on the final flux of changing this fraction of failed core collapse supernovae. And here you can see just a few examples of our benchmark cases of how the flux changes as a function of the fraction that we set. So if we then look at the final signal, so we have to take this time-integrated spectrum convolved with the supernova rate and to convert it into gamma rays, expected gamma rays, by computing the probability conversion. We do that for a typical galactic magnetic field model that is used in the literature for axion-like particle searches, so the so-called Jensen and Farrar model. And this is the final diffuse signal that you would expect in photons from this diffuse supernova ALPs background. So this is an integrated signal between 50 and 200 MeV. And as you can see, there are specific features in space that this template leads you. And this is what we want to exploit and to look for. In the Fermi-LAT data, so the larger telescope aboard the Fermi-LAT, the Fermi satellite is taking data since 2008, and it has a great precision and a great angular resolution to resolve point sources and other type of contribution. As you can see, just by comparing the strength of the ALP signal, which is of the order of 10 to the minus 6 in these units, with the total photon collected, we have a very faint signal that we want to look for. So the question is how we can disentangle or constrain this faint ALP signal. And the way we tackled the problem was basically to apply standard methods that have been used in the past for looking for weakly interacting massive particles to axion searches. So to do so, you have to decompose your sky in different components. The brightest one is represented by detected sources, which are about 5,000 objects that you have to mask from your search. You have the bright diffuse emission that comes from the interaction of cosmic rays that are injected by cosmic ray sources into the interstellar medium and then interact with gas and radiation field, and this is called the galactic diffuse emission. And then you have also large-scale structures like the Fermi bubbles or loop 1 that you have to take into account when you want to perform searches for new additional contribution to the gamma ray sky. So how to combine all these components is basically through a fit that takes into account the spatial dependence of the components and their spectral energy. This is called a template-based fit to the Fermi-LAT data. And by doing this sophisticated analysis, we have actually mitigated the effect of the uncertainty on the interstellar emission model by optimizing the region of interest that we analyzed. And also we managed to use new techniques to push down the threshold of the low energy Fermi data that we can use. And so we started our analysis from 50 MeV, where the cosmic ray background contamination is very severe. So those are the constraints that we get in these ALPs axion photon coupling as a function of mass. This red line here is our constraint for our benchmark case. And what we actually have also addressed is the effect of systematic uncertainties that comes from our uncertain knowledge of the modeling. And while the strongest uncertainties comes from the uncertainty on the fraction of failed event on the galactic magnetic field model, we still have a total uncertainty which is less than a factor of 3. And our constraints are at the level of the ones from extragalactic supernovae that I've been showing before. So they are a factor of a few weaker than the supernova 1987A, but still they are stronger than the CAST laboratory bound and offer an independent way to constrain the parameter space, which does not rely only on one single event, as it is the case for supernova 1987A. So if we then go beyond the photon-only coupling, but we also consider how alternative couplings might affect the production of ALP supernovae, we then open up new production channels. So in supernovae, we can, if we consider ALPs coupled to electrons, for example, the production can go through electron Bremsstrahlung. But there are strong constraints, as shown also yesterday, on the ALPs electron coupling, and this suppress the production in supernovae as well. If we, on the other hand, consider couplings to nucleon, and in particular to protons, then the dominant production channel goes through nucleon-nucleon-Bremsstrahlung. And then we have, given the current constraints that comes from the delayed neutrino burst from supernova 1987A, we can have abundant production of axion-like particles if we consider this additional channel. So what we have done then was to consider ALPs coupled to photons and nucleons. And here, then the production, as I said, is enhanced by the nucleon-nucleon Bremsstrahlung channel. So here is the flux of ALPs produced by a typical supernova, and the gamma ray flux from a supernova at the position on supernova 1987A, where you see that the Primakov production channel that I discussed before is very much suppressed, and the dominant contribution, if you allow coupling with nucleons, is then the nucleon-nucleon Bremsstrahlung. Of course, it depends on the value of this parameter, which we set at its upper limit. So this means that one can re-evaluate the limits from supernova 1987A, and also re-evaluate the constraints from the diffuse supernova axion-like particle background. So if we do so, then by using only the spectral information from Fermi-LAT data, so just some published spectrum of what is called the Fermi-LAT isotropic diffuse background, then we can set constraints on the diffuse supernova ALPs background, which do improve by 2 orders of magnitudes if we consider and open up the possibility to have enhanced nucleon-nucleon Bremsstrahlung production. While for supernova 1987A, We can also reevaluate the bound by including the enhanced production through nucleon-nucleon-Bremsstrahlung, and this would push by far this constraint and touch couplings which are of the order of 10 to the minus 4 GeV to the minus 1. So if you consider this additional production channel and heavier ALPs, then what occurs is that the conversion probability is not efficient any longer because it degrades with high masses. But what happens is that you open up the possibility for the axion-like particle to decay into 2 photons. And this goes as the mass of the ALPs to the cube, and so it becomes more and more efficient for heavy ALPs. So if you consider ALPs between 10 and 100 keV, then you can use COMTEL data, which are in this hard or let's say soft gamma ray regime, and is a previous, a very old mission from the point of view of the gamma ray astrophysics history. And you can set constraints for these masses on your parameter space. If you do not consider any coupling to nucleons, notably to protons, then you can close up a small gap between the HB cooling bound and the supernova 1987A bound, while if you allow for enhanced nucleon-nucleon-Bremsstrahlung production, then you can carve into the parameter space down to very low couplings for masses of the order of the MeV. Likewise, once you start considering other types of couplings, as for example the coupling with electrons, then we have said that the production in supernova is led anyhow by nucleon-Bremsstrahlung, if you consider the current bounds on the electron ALPs coupling. But if you have heavy ALPs particles, then what occurs is that you open up the electron channel for decay, and depending on the mass and the coupling for heavy masses, you have that the decay into photons is suppressed with respect to the decay into electrons. So for this particular part of the parameter space, you have the production that goes through the nucleon-Bremsstrahlung and the, let's say, signatures, the observable signatures that is led by the electron-positron pair decay. So what we did in a work led by Giuseppe Lucente was to investigate what is the positron production given by supernovae in the galaxy and what are the observable signatures. So this was also explored in the past, but what occurs is basically if you have a supernova and you have a light particle which interact weakly enough to escape the supernova envelope, then this particle can propagate into the interstellar medium. And when it decays into electron and positron pairs, those electron and positrons, then they propagate and they undergo, they are slowed down by the interactions with the gas and the ambient nuclei and electrons. And finally, they may slow down at the point that they annihilate at rest. And this annihilation at rest leads to a very specific signature, which is the 511 kV line, which for which there exist observations by the spectrometers aboard the integral satellite. So the condition for propagation and the length of propagation are quite well uncertain because they depend on the kinematic of the decay and also on the condition of the interstellar medium. So what we did, first of all, was to compute the number of positrons that you would get injected into the interstellar medium after the ALPs escape the supernova envelope and decay in the interstellar medium by being still trapped in the galaxy. And this is what you get, the number of positrons as a function of the axion ALPs electron coupling, where and at low couplings, basically the particles escape the galaxy, then there is a plateau where all of them remain trapped and efficiently escape the supernova envelope, and then for two strong couplings, you have that they are trapped within the supernova and they cannot escape any longer. So by computing this total rate of positron production, then what people have done was to use this total rate of positron production to set a bound on the ALPs electron coupling based on the observation of integral, but we went a bit forward. So what we did was actually to compute the signal in 511 keV photons that we would expect from a galactic population of core collapse supernovae. And to do so, we convolved the signal, so these two photons annihilation, with the distribution of type 2 supernovae in the galaxy in order to obtain in this latitude-longitude map projection what is the expected signal of 511 keV photon. And this map has a specific signature, which are these symmetric shape that comes from the distribution of the type 2 supernovae, which is peaked in the spiral arms of the galaxy, but is also a smearing which is related to the decay length and the positron propagation. So we studied this smearing parametrically by setting the smearing to 1 kiloparsec, because this is well justified by 511 keV line works, but is one of the main uncertainties that affects the final bounds. So with this prediction at hand, what we could do then was to compare the 500 keV line expectation from the ALPs supernova galactic flux with what has been measured by SPI. So the 500 keV line is a very specific signal, which is nowadays yet a mystery in high-energy astrophysics, because it's a signal which is peaked towards the galactic center, and you can also see that in this longitude profile of the signal, where you can see that the data are peaked towards the galactic center. And what we exploited was the fact that instead for galactic supernovae, you have a much shallower signal. So we set conservative bounds on the ALPs electron couplings as a function of the ALPs proton coupling by comparing this longitude profile of the data with our expectations. And the limits are here, and they depend slightly on mass, and there are also uncertainties related to the progenitor mass and the positron propagation length, as I mentioned before. Additionally, what you can also consider to carve a bit more down in the parameter space is the fact that if you consider all past core collapse supernovae, for each of them you would expect a 511 keV signal, but this time this signal would be received a redshift with respect to emission, and so would lead to a diffuse emission from all extragalactic core collapse supernovae, and you can constrain this diffuse emission by using the data from the cosmic X-ray background. So the cosmic X-ray background is a diffuse background in X-rays that has been measured by several instruments and mapped over a broad range of energies, and can be used to set limits in this parameter space, pushing further down the constraining power of these diagnostic tools. So the same argument of galactic supernovae can be applied in general to any weakly interacting particle that can be produced through mixing with standard model particles within the supernova envelope, and then have feebly coupling to escape the envelope. So what we have done was also to apply the same rationale to sterile neutrinos and their photons, obtaining quite constraining results. So what about the future then? So we mentioned before, the smoking gun signature possibly for ALPs from Corcolab supernovae would be this gamma ray burst peaked at hundreds of MeV. However, if we compute the chance for the large area telescope to have one detection within its field of view in the next 7 years, people have computed that this is about 3%. So Meyer and collaborators have assessed what would be the sensitivity of the LAT to a future supernova explosion in our galaxy towards the galactic center, but also in external galaxies like Andromeda. And the bounds the sensitivity that you can achieve is about a factor of 2 orders of magnitude lower than the current bounds from supernova 1987A. So the future for gamma ray search is, to me, is actually bright in a sense that it can be exploited on two sides. One hand is the low energy end. If we have a future MEV mission flying, then we would be able to better resolve the gamma ray background and also to get accurate spectra look for supernovae gamma ray ALPs, and this will constrain mostly the low end below, let's say, the nanoelectron volt, while at high energies, there is currently an unexplored part of the parameter space where the bounds almost all the grades, around 10 to the -7 electron volts in mass, where the Cherenkov telescope array and other high-energy telescopes can look for axion-like particles. And in particular, if we refer to searches for gamma-ray bursts, there is, to me, a quite relevant synergy between what these telescopes can do and optical transience facilities like Rubin ZTF to set, actually, to give a clock for the gamma ray search. So to come to my conclusions, I hope I conveyed the message that looking for axion-like particles with high energy astrophysics is a multi-wavelength approach, at least for X-rays and gamma rays, and radio will be touched upon in the following talks. We get from high energy astrophysics quite strong constraints on axion-like particles, and in the future we have the chance to improve by far the sensitivity to axion-like particles in the nanoelectron volt to microelectron volt mass range, and in general to all feebly interacting massive particles that may come from Corcolab supernovae. So thank you for the attention.
I do applause. Thanks, Francesca, for the very nice talk. Is there any question for Francesca from the audience? Otherwise, I will then start with questions. But let's see first if there is any question from the audience. You can raise your hand, and I will. Okay, Sam, go ahead.
Yeah, thank you, Francesca, for the nice talk. I had a question about the slide you showed just, I think, 2 or 3 slides ago on the projections for Fermi-LAT with the galactic supernova. There seemed to be the 2 lines, one corresponding to a supernova in the galactic center and one corresponding to Betelgeuse. And they have this trade-off behavior at low masses. And I was wondering if you could explain what exactly is happening there. I sort of naively would have thought Betelgeuse being so close would always be the stronger source.
Yes, you are right. And now I don't want to spoil this plot, but I think the 2 are switched. So I think Betelgeuse should be this dark blue line, and the galactic center should be the light blue one.
Okay, perfect. Thank you.
We have tried to redo the analysis, and this is what we are finding. But
okay, thank you.
One thing, if I can add something though, the non-triviality there, even if you switch, are still non-trivial in some ways. So there is also one thing is the magnetic field in the direction of Betelgeuse that was used in that paper. So it's a peculiar magnetic field, and also the distance, trivially, the distance goes away when the mass is very low. So it's not a Betelgeuse. Being when you're close enough, being closer doesn't help too much. So if you are closer than 1 kiloparsec or something, being 100 parsec or 200 parsec doesn't help much, because this is not a flux that goes down. I mean, the flux obviously goes down as distance square, but then you get longer magnetic field. And if you can assume that the magnetic field is roughly uniform, this square goes away. So it becomes a little bit not obvious what happens, right? So that also explains the features.
Right. So you're just saying that as long as you're talking about distance scales larger than the coherence length of the magnetic field, then that distance scale applies. And if you're smaller, then it's sort of irrelevant.
Mm-hmm. Yeah.
Very nice. Okay. Thank you. I appreciate that.
Thank you.
Okay. Any other question for Francesca? Otherwise, I have one. Okay, I can go with one, and then if anyone like shy can raise his hands. Actually, no, Georg, go ahead, Georg. You are not shy.
I have a probably very simple question. So about this electron-positron production, and then the positrons downscatter and exact, and then form this line. But does that happen to all of the positrons? Is this I mean, so is the total flux? I mean, do some of the positrons survive and just survive as cosmic positrons or something? And the other question related to this is, in every collision, when these electrons or positrons hit something, you also get Bremsstrahlung photons, right? Of course, you're down by a factor alpha, but it happens several times. And I mean, is that important, or have you checked, or maybe it's negligible? All the gammas that you get from these collisions. I mean, you get some cascade or something, you know. You can produce photons and so on. So are these could these be important as well?
So there were two questions, right? So the first is how many of those positrons emitted by decay thermalize, and no, we didn't. I mean, we assumed that all of them thermalize, and then only 25% go into this two-line process, while this is well known. I mean, the formation for parapositronium is kind of measured by 511 keV line observations, and while the other 75% goes into 3 photons, so contributes to the diffuse. But to compute really what is the total number of positrons that thermalizes, that you would need to have the full kinematic of the emission process and the kinematic of the propagation. However, for the second question, what if basically the secondary photons that are produced by interaction of those positrons with the interstellar medium, if I understand correct, can have a sizable effect on the final flux? I think the answer is basically no, in a sense that I did a similar computation for electron and positrons emitted from primordial black holes. This is a completely another way to inject, but just to address the effect of the secondary photons, what happens is that in the end, the secondary photon flux is dominated by what kind of reacceleration emission process you allow in the galaxy. And so if you want to set a constraint on the production mechanism, basically those secondary photons do not help much, because they only probe the propagation conditions. So in the end, they would not add much to the constraining power, and they can be neglected. And this should not depend on what, I mean, as long as you have 100 MeV positrons injected, this does not depend on the source. So is in the end the standard model physics of the interaction with the ESM. Just
for my intuition, this physics happens very close to the supernova. I mean, that must depend on how large is the decay rate, but should we picture this to be rather close to supernova, and then these charged E plus or minus are kind of trapped by the B fields around, or are we thinking about something much further away in the interstellar medium, I guess it must depend on the decay on the mean free path.
It depends on the decay length partly, and on the propagation. But here we consider more or less decay length and positron propagation to be of the order of the 1 kiloparsec, and you get this mirroring, so you can also get fluxes that are farther away from us. Of course, if you have longer propagation length, like I don't know, 5 kiloparsecs, which already sounds a bit unrealistic given the horizon for electrons and positrons, you can have transport which is much efficient through the galaxy.
Okay, thanks.
Okay, actually now with my I have a question and a comment actually also. First the comment just briefly, like, because you mentioned at the beginning, Rod, about when you were talking about diffuse, also like gamma rays that you try with different progenitors and also how this affect. But for example, in the work that we have done with Edoardo and Georg, I think that we have a nice, if you look at the data, right, even from Comte, like Fermi-LAT, and you plot omega square and the flux, okay, those data are kind of flat, okay, like in that kind of window that you would probe with typical energy from supernovae, right? And then if you take some typical like quasi-thermal flux with whatever power law, like or exponent or typical energy, right? Then the maximum of the distribution is not really dependent on the temperature of the core. This is basically what is determining, at the end of the day, whatever, it is also one of the nice thing about the supernova and what you probe, right? Whatever have you for your progenitor at the beginning, right? Radius, masses, whatever. The important thing is the temperature at the end, right? And so what we found is that what you measure then in the flux is not that sensitive to the condition and the temperature, so your flux of axion, and the main uncertainty is still the number of core collapse supernova that you also mentioned, no? If you assume like Madao, you know, stellar formation or Robertson. So that is really the one. While, for example, the redshift distribution or the axion flux do not play an important role. I think that, you know, there's also, for back on the envelope is something that is interesting. And while it is true that this core collapse, of course, is the main uncertainty up to factor of 2, right? And then I have a quick question is about your slide 35, if I remember correctly, about the electron coupling. It's a very quick question. I didn't understand why there is this. This cannot be physical, right? There is a cutoff of some coupling, and I don't understand why there should be an hard cutoff in the bound here, right? In the
here at the left.
Right, exactly. In the far left, it seems like an hard cutoff. Why so? Everything should be smooth, right?
Yeah, in my understanding, this is so now I don't know if this is an effect of the sampling of the bounds, but anyhow, there is kind of cutoff due to the fact that you do not produce enough ALPs any longer to sustain the.
But it's never a cutoff, no?
The positron,
right?
It's
never yeah, exactly. This is what I mean. Like it's never even when you have kinematical threshold, it's never a cutoff, right? Should go something, right? I guess so. I mean, maybe there is something that I'm missing, but typically, even if it is all all the flux should round, right?
Yeah, should be an issue with the sampling.
Okay.
I don't know if
Maurizio.
No, I think Pierluca is not here. I remember discussing it could have been just numerically heavy.
Okay, just numerically.
Because I remember these discussions, and if I was checking if Pierluca would be the best to answer.
Okay, I will email him.
You can ask him, but I think it was really a numerical difficulty.
But you can see it by the fact that the cutoff is a fixed GAP, so it's fixing. So it means that basically the problem is with the production from the supernova. So you see that probably they couldn't sample so precisely the couplings in the product that determine the production.
But this is weird because like this, like the free streaming, no? This
exactly.
Right?
Yeah, exactly. But then the point is that you have to reduce it a bit, and then you must have a slightly larger GAE so that you can still have something visible. So there is this trade-off in between.
Okay, just numerical. Okay, sorry.
But just considering there was nothing here, we thought that.
Okay, yeah, good, good. Okay, I don't see any further questions, so we can thank Francesca again for this very nice talk.
Thank you.
Now we pass to the second speaker of the evening,